In our physical properties of alcohols podcast, we're going to talk about the boiling point and the melting point of alcohols, as well as their solubility in water in conjunction with the hydroxyl group itself, and how having a hydroxyl group in your molecule is going to change some of those physical properties for what would otherwise be just a hydrocarbon. All right, so let's start by talking about the hydroxyl group and what that does to a molecule. Hydroxyl groups are polar. So remember from Chem 1201, we would look at shared electrons between two elements. And remember that we also said if the element is the same, your electrons are going to be shared equally, and it would be a nonpolar covalent bond. The exception to this is carbon and hydrogen. The difference in electronegativity is so small that these guys are considered to be sharing those electrons equally, and the bond is nonpolar. Well, in a hydroxyl bond, covalent bond, you have electrons that are not being shared equally. In fact, your oxygen is more electronegative than your hydrogen, so it's pulling those electrons closer to it. Hence, it takes on that slight negative charge, and the electrons are further from hydrogen, so it takes on a slight positive charge. And it's these slight charges that contribute to the properties of solubility for our alcohols. So just the presence of this hydroxyl group is going to allow low molecular weight alcohols to be soluble in water. This is the first time we've talked about something that is a low molecular weight. When we say low molecular weights, we are referring to the number of carbons. And that's important to note because we'll reference that terminology again. So low molecular weight alcohols are going to be alcohols that have 1 to maybe about 4 or 5 carbons. These are soluble in water, and it's due to that hydrogen bonding in your hydroxyl group. And that is due to the difference in electronegativity. So looking at our diagram down here, we know oxygens are taking on a slight negative charge, and our hydrogens are taking on a slight positive charge. So these are going to be attracted to water molecules. So we have the formation of hydrogen bonding anytime you have an oxygen present in a hydrocarbon or a hydroxyl group present in a hydrocarbon, and that's going to contribute to those properties of solubility. As we increase the number of carbons in our alcohol, the hydroxyl group is going to lose its effect, and so therefore it's going to have less solubility in water. This is a general note, and you're going to see varying scales, but 5 or more carbons are typically not soluble in water. All alcohols are soluble in organic solvents. So I do want to note that in lab, this is not like a cutoff point. It's not like 4 carbons is soluble and you're not going to get any layers, and 5 or more carbons is insoluble. There's kind of a gradation to it. So you're going to get right around the 4, 5, and 6 carbon level. You may tend to see a little bit of slight solubility there. On the previous slide, we talked about what effect the hydroxyl group has on the solubility of an alcohol. Now let's talk about what this does to the melting and boiling point, having that presence of a hydroxyl group. So we know that alcohols have higher boiling points than alkanes of similar mass. Keep in mind, anytime we mention mass, we're really just talking about the number of carbons in the parent chain of the alcohol. So if you were to compare a single carbon alkane to a single carbon alcohol, alcohols are going to have a higher boiling point. And the reason they're going to have a higher boiling point is simply the presence of your hydroxyl group. So remember that an OH group has hydrogen bonding. This is the strongest intermolecular force. So that means that you are going to have hydrogen bonding between 2 different molecules of your alcohols, and those are going to be held together more tightly than, say, the London dispersion forces you may see in just a hydrocarbon like an alkane. Because of this stronger attraction between molecules, it's going to take more energy in order to get them to separate from one another and to change state, so to go from a liquid to a gas. So therefore, their boiling points are higher. And I just want to show you this diagram on the bottom because it compares butane, a hydrocarbon, all carbons and hydrogens. Remember, these are going to have London dispersion forces, the weakest of the intermolecular forces holding them together. Here is an ether, ethyl methyl ether. So this is just an oxygen. And remember that an oxygen and a carbon are going to have a polar bond between them. So we are going to get dipole interactions, not the strongest, but they're certainly stronger than London dispersion forces. And we see that in the difference in the boiling point. So butane is going to turn to a gas at negative 0.5 degrees Celsius, whereas ethyl methyl ether, having dipole forces, is going to have a higher boiling point at 11 degrees. If we were to compare that to a 3-carbon alcohol, 1-propanol, the presence of that hydrogen bonding, look at what it does to the boiling point. Now we're not turning from a liquid to a gas until 97 degrees Celsius because we have hydrogen bonding, and that's causing those molecules to be held closely together. On another random note, phenol, that is our aromatic alcohol, benzene with an OH group, is soluble in water. So despite having 6 carbons and a lot of nonpolar portions to this, phenol is still soluble in water. So it's kind of bucks the rule to, you know, all alcohols 5 carbons or more are going to be insoluble in water. This will be your exception. We're going to kind of explore that more in lab. All right, I wanted to go through some of the health notes that your book had on interesting alcohols. The first is a single carbon alcohol. This is methanol, also known as methyl alcohol. Methanol is a useful solvent for chemists. It's also one of the starting materials for the synthesis of plastics. So it's something that we see a lot in industry. Methanol can also be found in distilled spirits. It's one of the byproducts of distillation. It's something that you don't want in your distilled spirits. It's not the good kind of drinking alcohol. Your liver will metabolize methanol into some pretty harmful products and can actually lead to blindness. It can lead to eventually death with as little as 15 milliliters. I'm going to write that down. 15 milliliters, death. Whoa. So it's something that we have to certainly test for anytime that we are distilling spirits, if we're making whiskey or anything else that's distillation alcohol. We have to make sure we're not killing our customers. So that's something that has to be tested for. The next one, you may not recognize it in the ball and stick form, is isopropyl alcohol, also known as rubbing alcohol. Isopropyl alcohol it used to be used as rubbing alcohol. It used to be used to, you'd rub it on babies who had high fevers, and it would evaporate quickly because it doesn't take much energy to get it to change from a liquid to a gas form. And as it evaporated off of the baby's back, it would cause that cooling sensation, that evaporative cooling. It's not something that we use anymore, though. You don't want to rub your baby down with rubbing alcohol. Nowadays, we use it to clean the site of an injection. If you're going to get a flu shot, we'll rub a little isopropyl alcohol in there because it's going to kill every living thing on the skin and prevent infection. This last one that you're looking at is glycerol. Glycerol is kind of a funny thing. Glycerol is found in just about everything. It's found in soaps, liquid soaps, lotions. We find it in shaving cream. It's non-toxic. It's also found in candies and other prepared foods. It has the presence of multiple OH groups. So it's water soluble and it will bond to water, so it's going to help retain moisture, which is why we find it so much in lotions and products that you would put on your skin. It's going to be a moisturizing ingredient. All right, so let's talk about our favorite alcohol, or at least the one we have the most contact with as humans. That's ethanol. Ethanol is the drinking kind of alcohol. We get ethanol when glucose, a simple monosaccharide, is digested by yeast. It goes through cellular respiration. The yeast uses glucose as an energy source, and in anaerobic conditions, or conditions without oxygen, the yeast are going to produce ethanol and CO2. So this is how we get the alcohol in wine and beer, and that's how we also get the carbonation. And not all drinks we retain the carbonation, such as wine. We let that CO2 out of the container so that we have a non-carbonated wine. If we keep it, we might have something like a bubbly champagne. Humans and ethanol go back 4,000 years. We have a very long relationship with this particular molecule. We use it a lot in lab as a solvent. However, lab grade ethanol is not good to drink. If you're thinking this would be an easy way to go grab a jug and have a party on a Friday night, do not do that. There are additives like benzene or methanol that are added to lab grade ethanol to discourage drinking. So it'll make you very, very sick. Remember that wine and beer and liquor are not pure ethanol. That would be insane. They're actually cut with water. And from that, we get our ABV values, or alcohol by volume values. Beer is going to be about 3 to 8% ethanol. Wine is going to be 10 to 14% alcohol, and liquor anywhere from 35 to, oh my gosh, you be careful, 90% alcohol by volume of water.